Hey guys, so welcome to Chapter 15 lecture. Chapter 15 is all about chemical equilibrium. Now, some reactions go to completion, meaning that all the reactants turn into products. And for the most part, we've mostly been working with those types of reactions when we write and see chemical equations. So for example, an example of this would be the hydration of sodium chloride in an unsaturated solution. We take let's go with green, some solid sodium chloride, and when we add it to water, H2O here above the arrow, it dissociates completely into sodium ions that are aqueous and chloride ions that are aqueous. So all of the sodium chloride presumably dissociates. But some reactions only go part way to completion, and then they reverse themselves, and we call these reversible reactions. And this can happen to sodium chloride in the case of a saturated solution. If you add a whole bunch of sodium chloride to a solution, right, some of it will, or a lot of it will dissociate into aqueous ions. All right, but if it's saturated, there's not enough room in the solution for all of them to go into this ionic state, and some of them will be dissociating while some of them will be reconnecting to form ionic compound sodium chloride. So this is an example of a reversible reaction. It's going in both directions. The dissociation and the precipitation reactions are both occurring. And we talked about this in the chapter on solutions, and that this is a dynamic equilibrium situation. So we represent equilibria with this reversible arrow. The arrow pointing to the right represents the forward reaction, and the arrow pointing to the left represents the reverse reaction. And this whole thing represents a dynamic equilibrium. All right, and the definition of equilibrium, and this is important, is that the rate of the forward reaction equals the rate of the reverse reaction. All right, at equilibrium, it is not that you have equal amounts of solid sodium chloride and aqueous sodium chloride, okay? It's that the forward and reverse reactions, those rates of those two arrows, are equal at equilibrium. So another thing, let's just look at what a reaction looks like. That starts with some reactant. All right, we'll say reactant is green. So at the beginning of the reaction, you have a bunch of reactant. The concentration of the reactant is high, but over the course of the reaction, it reacts to form products, and that rate is increasing at first and then slowly decreasing and then sort of plateaus off. All right, so that you end up with this sort of constant concentration of reactant. If we look at the product side of the reaction, and we'll make products blue, initially we start off with no products, and the amount of product gradually rises and then ultimately also peters off. All right, so you'll notice that at equilibrium, when the rate of change is equal in both directions, you get this sort of the amount of products and reactants is not the same, so there's still a higher concentration of product than there is reactant at the end of this, or at equilibrium, but there's no longer a change in the amount of product or reactant. So the amount is staying steady, all right, because the forward and reverse rates are the same. So it's not that the amount of product and reactant are equal, it's that the forward and reverse rates are equal. And at equilibrium, the amount of the reactant and product is no longer changing, all right? But the amounts are not equal. And that's a common mistake in chemistry, that people think equilibrium, they think of the equal as equal amounts, but it's never equal amounts. It's simply equal rates and a constant state of no change in products and reactants amounts. All right, so we can, for any given reaction, this ratio, basically, of products to reactants at equilibrium is constant. And we call this the equilibrium constant. And you're going to love this. It is demonstrated by a letter K, a capital K. as opposed to the little k, which is the rate constant from the previous chapter. I don't know why chemists love reusing letters so much, but big K is the equilibrium constant. I suppose K is a convenient letter for constant since it makes a K sound. All right, so the equilibrium constant is just the ratio at equilibrium of the concentration of the products divided by the concentration of their reactants. So it looks like this. K, and we'll put a little C here because there's another version of K we're going to talk about. This one is based on concentration, so the C comes from concentration. And it's simply the ratio of the concentration of the products at equilibrium divided by the concentration of the reactants at equilibrium. All right, there are no units, by the way. K has no units, it's just a number value. So for a reaction, let's say we have a generic reaction of AA plus BB reacts in a reversible manner to form CC plus DD, where the lowercase letters represent numeric coefficients and the uppercase letters represent the chemical formulas. The equilibrium constant expression for this reaction would be that K sub C equals the concentration of the products, so C and D, raised to the power of their stoichiometric coefficients. So C has a little c and D has a little d, divided by the concentration of the reactants to the power of their stoichiometric coefficients. All right, so it's just basically taking that chemical equation and reconfiguring it into this ratio format. Not too difficult. Okay, so let's work an actual example with numbers too. So we've got this equation here. Hydrogen gas reacts with iodine gas to form two hydroiodic acid gas molecules. All right, so we've got initial concentrations in this first column. All right, initial concentrations of the hydrogen, of the iodine, and of the hydrogen iodide. And then in the second column, we have the equilibrium concentration. So when the reaction reaches equilibrium, what are those new concentrations? All right, so let's look here. In the first experiment, we start with 0.5 molar of each of the reactants and no product. And then at equilibrium, we have a decrease in the amount of the reactants and an increase in the amount of the product, which we expect. We can calculate the equilibrium constant for this by setting up this equation here and plugging in the numbers of those concentrations at equilibrium. All right, it's important. The equilibrium constant uses concentrations at equilibrium. So these initial concentrations are just for reference. Okay, so at equilibrium, the product to its coefficient, HI squared, so that's going to be 0.78 squared divided by the concentration of each of the reactants. And they have no coefficient, so there's no power to raise them to. So it's going to be 0.11 times 0.11. All right, and when we do the math, we calculate this 0.78 squared divided by 0.11 squared, essentially, is 50. Okay, so let's do it. Let's start with totally different concentrations. This time, we have no reactant, and we have 0.5 molar of the product. So now we're going to run the reaction in reverse. All right, so we do that, and we end up with increased concentrations of the reactant, decreased concentration of the product. So we still can plug in using the same equation. All right, still, even though we're going in reverse, this is still the product. So we still have it on the top of the reaction, 0.39 squared divided by 0.055 times 0.055. Do the math. K turns out to be 50. Same as we got before. Give you 3 guesses on what the answer to this third one's going to be. So in this one, we start with equal amounts of H2, I2, and HI. We run the reaction, and at equilibrium, we measure the concentrations of each. We plug into the equilibrium constant expression. Our product concentration at equilibrium is 1.17 squared, and each of the reactants 0.165 times 0.165, and we still get 50, all right? Which is why this is called the equilibrium constant, because it's constant. No matter what conditions you start with, no matter what concentrations of reactant and product you start with, at equilibrium, you will always end up with the same ratio, which is what the equilibrium constant represents, okay? So that's what this is saying here. No matter what the starting concentrations are, the ratio of product to reactant is, which is the equilibrium constant, is always the same. Constant. All right, let's try a practice problem. Consider the reaction. Nitrogen gas plus 3 moles of hydrogen gas react to form 2 moles of ammonia gas in a reversible way. In this equilibrium, okay, so we've got an equilibrium mixture of this reaction at a certain temperature, we don't care what temperature right now, has an equilibrium concentration of N2 is 0.115 molar. The equilibrium concentration of H2 is 0.105 molar, and the equilibrium concentration of the NH3, the product, is 0.439 molar. What is the value of the equilibrium constant Kc? So the first thing we want to do is just write out what is the equilibrium constant expression. Just convert this formula into an expression. So we want products to the power of their coefficient, so that's going to be squared, divided by reactants. The 2 reactants are N2 and H2. N2 does not have a coefficient, or has a coefficient of 1, and H2 has a coefficient of 3, so we're going to put that 3 up there. All right, so now all we have to do is plug in the values we're given in the problem. So the concentration of NH3 is 0.439 molar, square that, divided by the concentration of N2, which is 0.115 molar, times the concentration of H2, 0.105 molar, and this one is cubed. So now we do the math in our calculator, and we get 1.45 times 10 to the third. Remember, K equilibrium constant does not have any units, so that is the correct answer to 3 sig figs. Okay, so far we have been working with what are called homogeneous equilibria, in the sense that all of the materials in the equation have been gases. But sometimes we have heterogeneous equilibria, which contain multiple states: gases, liquids, solids, aqueous, so on and so forth. Well, those are all of the options. All right, so the thing is, the equilibrium constant expression is based on concentrations. That's what the brackets are, if I didn't remind you that before. The brackets represent concentration. So which of these states can have a concentration? All right, a gas can have a concentration. You can have different numbers of moles per liter of a gas. Pure liquids do not have a concentration. Pure water does not have a concentration. Only when we add something to it and it becomes a solution, aqueous, does it have a concentration. All right, so only gases and aqueous things have concentration. Solids and liquids do not have concentration. So therefore, since concentration is what goes into this formula for the equilibrium constant, only gases and aqueous substances will affect the equilibrium. If one of these substances is a solid, the amount of it is not going to change the equilibrium. And we'll see that in our equilibrium constant expressions. So let's practice an example problem with a heterogeneous expression. So we've got 2CO, which is a gas, reacts to form CO2 gas, and carbon, which is solid. All right, we'll make that different, okay? So remember, solids do not have a concentration, so they're not going to go in our equilibrium constant expression. The equilibrium constant is the products over the reactants, but only it's the concentration of gas or aqueous products over gaseous or aqueous reactants. All right, so in this case, the only gaseous product is CO2, and the gaseous reactant is CO, and it has a coefficient of 2, so we bring that coefficient up and we make it squared, okay? So carbon the solid carbon is not part of this equilibrium constant expression, okay? It's just left out entirely. So if you were asked to give the equilibrium constant expression for this reaction, this would be it. All right, so let's practice this. We'll express the equilibrium constant or write the equilibrium constant expression, either way, for each of the following equations. So the first one, what I like to do is go ahead and first make note of what the state is. All of these are gases, so I'm underlining them in green. They're all go for the equilibrium constant expression. So for this equation, the equilibrium constant expression will simply be products, CO, and H2 squared over reactants. And this reactant, CH3OH, that is a single substance. Sometimes people want to split it up into like CH3 and OH, but don't do that. This is one molecule, one formula. So that's the equilibrium constant expression for the first one. The second one, we've got, this one's a solid and another solid and a gas. So the only one that's going to go in our equilibrium constant expression is the CO2. So the equilibrium constant expression for this one is simply product, concentration of product, CO2, over a concentration of reactant. There are no reactants that go into this equation, and the other product does not either. So the equilibrium constant expression for this reaction is simply dependent on the concentration of the gas, CO2, that's produced. And then lastly, for this last equation, we've got a gas, a gas, a gas, and pure liquid. Liquids, remember, do not have concentration unless they are solutions, and then they are aqueous. So the equilibrium constant expression for this is going to be product, our product concentration of the product, which is Cl2, with a coefficient of 2, which becomes the exponent, divided by the concentration of the reactants, HCl to the 4th power, and O2. All right, so remember, make sure that you are making the coefficient is, not this one, is what becomes the exponent, okay, not the subscript. All right, the subscript is part of the chemical formula. So O2 remains O2. We don't put that subscript as a power, okay? It's only the coefficient in front that becomes an exponent in the equilibrium constant expression. So we know now how to write an equilibrium constant expression. Easy peasy. It's just concentration of products over concentration of reactants. If there's a coefficient, you make that the exponent. All right, but what does this mean conceptually? What does it sort of mean? Can't find the word I'm looking for. All right, so if we look at this mathematically, if the equilibrium constant is just a ratio of the amount of product over the amount of reactant, all right, if the numerator, the top number, the amount of product is very large, then this ratio is going to make a very large number. It'll be a number that's greater than 1 anyway. So if K is greater than 1, that tells us that at equilibrium, we have more product than we do reactant. All right, so another way to say that is that product predominates. So you could be given a simple question that's like, the certain equilibrium reaction has a K value of 2.8. Which predominates at equilibrium, product or reactants? All right, and if the value of K is greater than 1, it means that the product predominates. So this would be a value of greater than 1. If the amount of product and reactant is the same at equilibrium, which is very rare, that's not very common, then K will equal 1. So if K equals 1, it means the concentration of product equals the concentration of reactant at equilibrium. So it looks something like this. All right, so that would be a K of equal to 1. If there is a very large amount of reactant left over at equilibrium and not a whole lot of product formed, then the denominator is going to be larger, and that means K will be less than 1. So if K is less than 1, then reactants predominate. Or in other words, when you reach equilibrium, you have more reactant than you do product left over. So this would be a K of less than 1. All right, so we can look at this graphically here, all right, and indicate the value of K. So if, let's call the reactant blue and the product green. So just to clarify these, the reactant is what we're generally going to be starting with. So I'm going to say this is the reactant line, the one that we're starting with, and that this is the product line, the one that we are making over the course of the reaction, assuming these are all going in the forward direction. Okay, so in this case, in A here, we have more product, so equilibrium sort of starts, we reach equilibrium when these lines become parallel, when the amount of product and reactant is no longer changing, when the slope is 0, meaning the rate is equal. Okay, so in this one we have more product than reactant, so that means that we have a K of greater than 1. In this one, all right, we reach equilibrium somewhere over here. The lines become parallel. The amount of product and reactant is no longer changing. But in this case, we have more, I did this one wrong. Blue line is reactant. We have more reactant than we have product. So this one has a K of less than 1. In this one, we have more product than reactant. So this one is a K of greater than 1. And in this one, our product and reactant reach equal amounts. And so in this case, this would be a K equal to 1. Okay, so you could have questions that give this to you in a graphical form, whether it be a line graph like this or a bar graph like this, or in terms of numbers, it could give you concentrations of products and reactants at equilibrium, and then ask you, is the K going to be greater than 1 or less than 1? And you can eyeball that. So when we work with equilibrium constants in chemical equations, there are some manipulations as sort of seen in chemistry, as we've seen in a couple of chapters. We know that reactions sometimes happen in stepwise fashion, and that we can add those steps together to get an overall reaction. We saw this in kinetics, and we saw this also in thermodynamics. We were able to add reactions together, and we could also add their enthalpies together. So we're going back to this sort of theme of being able to look at steps of reactions and then add them together to get an overall reaction. So when we're doing this and we're manipulating the equilibrium constant, there are some rules for how we do that. All right, so the first rule is if you reverse the equation, then you invert the K, the equilibrium constant. So the K for the reverse reaction is 1 over the K for the forward reaction. So for example, if we have this reaction here, A plus 2B reacts to form 3C, the equilibrium constant expression for this would be product C cubed divided by reactants A times B squared. If we reverse this reaction, all right, and flip it, then we have to flip that K, or invert it is the term in math when we flip the numerator and denominator. All right, so that, makes sense. It fits with our new products are A and B, so now the numerator in this K is A, B squared. All right, so if we were given values, let's say we were told that the K for this equation was 30, all right? That means that the equilibrium constant K for this equation would be 1 over 30, all right? Which is what, 0.03? All right, number 2. The second rule is that if you multiply the equation by a factor of n, 1, 2, 3, whatever, then you raise the equilibrium constant to the power of n. So if you multiply the whole equation by some factor, then you have to raise k to that factor, right? And this will make sense too when we work it out. Okay, so for example, if we have A plus 2B reacts to form 3C, and we multiply that equation by 2, all right, then we multiply all the coefficients by 2, we get 2A plus 4B equals 6C. So the K for this equation is C to the third concentration of A, concentration of B squared. All right, and then this one is K equals C to the 6th power over A squared times B to the 4th power. All right, so notice that all we did was take this equation here and square it to get this equation down here. Okay, so in other words, we squared K. So if this had a value of 45, then this one would have a value of 45 squared, which is 2025. Alrighty, third rule is having to do with if we add equations together. So if we add 2 or more individual equations to obtain an overall equation, then what we need to do is multiply the K's, the equilibrium constants of the individual reactions. So the rule is in this box here. If we add equation 1 and equation 2, then we're going to multiply the equilibrium constant from 1 times the equilibrium constant from equation 2. So let's look at this again and sort of derive this rule. So we have simple equation A reacts to form B, then 3B react to form 3C. If we add these together, overall we get A plus 2B, because one of these will cancel out with that. So we get 2B reacts to form 3C. And K1 here, so we'll just write out the new K. So we'll call this the overall or the third reaction. And if we just map out the equilibrium constant expression, we would get this. And this. All right, which is the same thing as if we multiply these two. If we multiply K1 times K2, all right, these cancel out, and we get this expression here, okay? Looks like I'm going to get cut off at 30 minutes, so I've got 20 seconds left. If reaction A reacts to form 2B has the equilibrium constant of K equals 0.01. What's the equilibrium constant for this reaction here. So notice that we had to reverse it and divide it by 2. So give that one a try and I'll give you the answer in the next video.